Hey everybody, so here is the third of the kind of lesson videos for this particular chapter. This one has to do with the concept of work and kind of how we apply work concepts to this particular stuff that's going on in here. Hopefully this will help you kind of get through this particular problem. This is now part of chapter 10, just so you have some idea of what section we are working on as we're getting through this particular part. So this last part, chapter 10, and then we'll actually get a little bit into chapter 11, is about work. This particular one's about the impulse momentum theorem and collisions and how they relate to that kind of stuff. And then we will also, actually this is really mostly about work. And then we'll also get into the last section will be about conservation of energy. Not in this particular unit, a video, a different unit that will end up, or a different video I'll record later. So here you go. If we're trying to apply force to an object, what happens if you're sitting there and like shoving on something? If I have my, my glass of water here and I'm pushing it on one way or another, the whole concept here is we would say that eventually if you apply enough force to an object, you're going to get that object to move. And most people would say, well, that takes energy to do that. And that's fine. That's actually a pretty good concept of what energy is. But we need to kind of back up a little bit before we start talking about what energy is or something else that we need, which is actually this concept of work, is the technical name for this. Work is when you apply force to an object and you move it through a distance. The particular concept of that is called work. So the equation for work is actually really simple. It's work equals force times distance. The units for work are a little bit funky. So I do want to kind of mention this in terms of what the actual units are as we're going through this. I gotta get my pen tool. Sorry about this. If we're doing work equals force times distance, work equals force times distance. That's an aggressively fat pen. Hold on, let me fix my pen here. There we go. So if we do work equals force times distance, force is in newtons, distance is in the unit of meters. And so we get a complex unit called a Newton meter, is a really weird thing. The other name for a Newton meter is also known as a joule, Joule, Joule is how we pronounce that. So the units of work, and that's actually the word that I have kind of hiding back here is what's the word for units? It's either expressed in the units of Newton meters, because force is in newtons and distance is in meters, or it's in joules. I'll remind you that a Newton is actually a complex unit as well, because force is mass times acceleration. We can actually get a different equation for work. Work equals m times a times d. So you can always say that work always makes you mad because it's mass times acceleration times distance, and that is the other equation for doing work. Mass is in kilograms, acceleration is in meters per second squared, and then distance is in meters as well. So that actually means what a joule is, or what a Newton meter is. It's really bizarre. It's a kilogram meter squared per second squared. Because you got kilograms times meters again, divided by second squared. Really weird. So again, you can see why we tend to call it Newton meters, is one way to talk about it. Otherwise, we typically call it joules, and that's the more commonly used unit of work that we end up doing. So when we're calculating work's actually a really easy thing mathematically, at least when we start. Again, work equals force times distance. Again, whiffed, force times distance. If we're talking about little Timmy here is pushing his car and he's moving at 3.5 meters, you've got 23.7 newtons of force, and then you've got 3.5 meters. Those are both standard units. Do I have a calculator? How do I end up losing my calculator all the dang time? All right, well, I use my phone. Sorry about that. So 23.7 times 3.5 is a pretty simple answer. It looks like we have two sig figs, so that would be 83, and that would be the unit of joules, or 83 Newton meters. Kind of weird, but they both work. The actual answer is 82.95. So anyway, with that two sig figs, that's 83 Newton meters, or 83 joules of work were done to move the car. Next question comes along is, does all work, applied force, do work? And the answer to this is actually no. We'll get to this in a second. So you can imagine that if I have to do my basic equation, work equals force times distance, there's a couple of things here that play a role. I can apply all the force that I want to. If my object doesn't actually move anywhere, then technically the answer is no, I did no work whatsoever. So if I literally sit there and push on a wall and push on as hard as I possibly can, break out into a sweat, hurt my wrist, whatever it is that I want to do. If that wall has not moved, no matter how much force I've applied, it actually hasn't done any work. And the second thing is that the way that I apply the force, this component of it is really important as well. It turns out that when we're talking about calculating work, work has to be done in the same direction as the movement itself. And so this is kind of a key idea, that if we have an applied force that's moving in one direction, Fa, and that we also have distance in that same direction, then all of that force is being turned into or being used to accomplish work. But as I said, for the example, this one in the middle, if I push a force, but there's zero distance that's being done, then our net work here would be equal to zero. The other ones are a little bit funkier, kind of a little bit more of a trick question kind of thing. So for example, if I pick up an object and then just hold it there. So for example, if I lift up my very not heavy phone here and then just hold it here, I'm actually not doing any work at this point at all, because I'm lifting it up. Well, in the lifting process, my force direction is up and my movement direction was up. So I do work in the lift, but the hold itself does not require any work whatsoever. I'm kind of doing some effort against gravity, but I'm not currently doing any work as long as it's not moving. That's the kind of the weird thing. So again, if my force is up, but there's nothing going on, then it doesn't work as well. Same thing, carrying my bag and walking to school. Now, this is definitely a little bit weird. I had to do work to lift it, but if I'm moving my phone this direction, I'm really not doing a lot of work to move it horizontally. Now, why is that? It's because my force is kind of in the upward direction, but the movement is generally horizontal. So if I've got, in this particular case, force is this way, Fa, but movement is this way, then those aren't working together. And again, technically that's not considered work. Yeah, okay, I understand. There's a tiny bit of work that's being done as I'm pushing my phone left to right, a tiny amount. But compared to the weight, especially if I'm lifting up a really heavy object, you do work against weight to lift it. But in order to move it forward, the work has already been done. Really, you're not doing any additional work to move it horizontally. Again, your work is being done against gravity. So again, this is a little bit of a weird thing when it comes to work, is that with work, the force and the direction of movement have to be in the same direction. And this leads us to our next kind of set of problems, which is when we're doing, come back here, when we're doing work at angles to it. When we are doing work at angles, there's my little funny cartoon for this one. When we're doing work at angles, we have to take vectors into account. If you're doing something like this person here is pulling a big heavy box across there, we get a slightly different version of this. So if we're moving the box horizontally in this direction, if I get my pen back, where'd it go? If I get my movement is this direction, that means only the component of force that's moving that same direction is working. In this case, Fa is at an angle. It's going up this direction, and not all of that applied force is doing work. Only the component of the force that's in the same direction as movement, in other words, the x component in this case, is the one that's actually doing the work. Now, sometimes it's the y component. If you're doing work, vertically, that's a different kind of situation. But because in this case, the distance is horizontal, dx, that means we can only use Fax in order to be able to do this. And so the short version of this is we're going to be using a cosine function, because cosine would give us our adjacent side of this particular angle. So a lot of times you will see this particular angle for equation for work, which is work equals force times distance times cosine of theta. I don't really like it presented in this particular form. Well, the way I really like it is F times cosine theta times displacement is a little bit better way to kind of think about it, because this is our applied force. The cosine of this angle gives us the x component, and then we're multiplying it times d. So I don't know why they usually do FD cosine theta. Maybe it's just a little bit easier way to write. So again, it's the component of the work, the component of the force that's in the same direction as the movement is the one that's actually providing work for us. So here's an example of this sort of problem. So here I am taking my poor cat for a walk. My cat weighs 2.5 kilograms. If I take it for a 43-meter walk by pulling it with 35 newtons of force at an angle of 42 degrees, how much work am I actually doing? So if I take a look at my particular thing right here, here's my picture. Here is my 42 degrees is the one I'm referring to. My applied force is 35 newtons, and I do know that my cat weighs 2.5 kilograms. It's actually not, my cat's way heavier than that. It's only about a 5-pound cat. My cat's like a 10-pound cat. So how much work am I doing? Well, In this particular case, work equals force times distance. But again, I know my distance here is 43 meters. For my force, I need to figure out what that particular value. Oh, speaking of cats, hello, cat. I should take this cat for a drag. But in terms of doing this, I can't just plug in the 35 here. The reason why I can't put the 35 in here is because that 35 is this direction and the displacement is that direction. So those two particular things don't work together. What that means is I do need to figure out which component of work has to be done here. So in this particular case, it's the x component of that 35 newtons. So I would do, oops, get my pen back, sorry about that. I would do the cosine of 42 times 35 would actually give me the component of work that's being done. Let's see if I can get that to work on my calculator here. Let's see, what am I doing? 42 degrees. Take the cosine of that times 35. And I get the component of force here is actually 26 newtons, 26.01. Again, don't forget to make sure that your calculator is in degrees, not in radians. Otherwise, you're going to get funky numbers. So again, this one is not right. My work here is actually 26 newtons of force in the x direction times 43. Is that right? Yep, times distance, 43 newtons. 43 meters is going to give me my total amount of work done times 43. And I would get, what? A big number, 1118.432. What in the heck do I do with that number? All right, so 2 sig figs looks like 1100 joules, or you could say 1.1 kilojoules. A lot of times you'll see them kind of reported in kilojoules as well. Remember that a kilojoule is simply 1,000 joules. So you'll see some of those kind of go back and forth sometimes in the book. A joule is not necessarily a ton of energy, so kilojoules is commonly done. Or you could write as 1.1 times 10 to the third joules would also work. Any of those work. Or you can call it Newton meters. Again, same thing. Newton meters, joules, those are completely equivalent amounts. Okay, moving on. What's next? Your turn. Take a moment and see if you can figure out the answer to this one. We've got little Timmy here, is pulling his little sister, whatever you want to call her. He is pulling the wagon 3.5 meters with a force of 12.6 newtons. And you can see from the picture right here that this wagon is not being pulled horizontally. It's being pulled up a little bit of an angle. We got 30-degree angle. So hit pause and see if you can work this out. I'll grab my handy dandy calculator and see if I can figure it out as well. Hit pause. Did you? You're lying. Okay, work equals force times distance. Again, I've got a 30-degree angle right here. So that means, 30 degrees like that. That means that I want to do the cosine of 30 degrees times my applied force. In this case, little Timmy is pulling with an applied force of 12.6 newtons. So I'm going to do 30. I'll do the cosine of that value times 12.6. I get an applied force of equivalent to about 11. We got 2 sig figs in here, so it's 10.9 right now, but it'll be 11 sig figs by the time we're done. So this would mean 10.9 newtons is the actual part of the force that's doing work, times 3.5 meters. Times 3.5, and I get an overall value in the end, 38.1917, plus exactly some change and all that, or 38 joules, 38 Newton meters. Either one works. Newton meters. There you go. So again, make sure that you're just remembering to take the actual component of the force that's doing the work. It's not going to prompt you to do that. You have to look at the diagram, make you do that. Make sure that you do that. What happens to the rest of the work? Rest of the force, by the way. The rest of the force, the vertical component of that force is, I call it convenient force. It actually is done to help reduce the strain on little Timmy's back, or my back as we're doing it. It actually also goes into normal force, and I've got a challenging little problem coming up here in a second that has to do with that. We do have the other forces on this. Remember, we've got something that's going downwards. If we start putting friction into these, we've got something like Fg. We've got an upward force here, Fay. And that's that part that's actually going to kind of go up against this way, which would be Fn. So again, that's going to be a little preview of another problem that we'll do here in a second. That force doesn't just disappear, but like I said, I kind of call it a convenience force more than anything else. It allows little Timmy to stand up, or me not to bust my back as I'm pulling something around. All right, moving on. Okay, so here's another example of take a moment and figure this out. Here we've got our little boy carrying his backpack up the stairs. And so this is a question that you need to do. He's carrying his 18-kilogram backpack up one floor using the stairs. The difference in height between the floors is 4 meters. The stairs are 7 meters long diagonal. So basically, here's what this means, is that you have basically a flight. Oh, crap. I could draw, that would be super helpful. Let's try some more time. So we have definitely a flight of stairs. It's like this. This is 7 meters. We know that it's basically 4 meters up between the different floors. I don't think this part is mentioned in terms of the horizontal tread that's on there. How much work is the boy doing to carry the backpack up? So this particular question, some of the homework problems is asking you like literally how much work is being done up the ramp, or is it just talking about how much work is the boy doing vertically? In this particular case, the way this one is worded, I'll give you the hint on it right now. The way I've got it kind of written in here, how much work is he doing here? What we're actually referring to is typically how much work is being done against gravity. We're almost always concerned with the vertical component of work, not the amount of work that's getting him, across. Because really what's happening in a flight of stairs, all a flight of stairs is a way for you to lift something more easily. It's a ramp, basically, is what you're trying to do. It's a ramp with a zigzag to it. But really the work that you're trying to do is up against gravity. You're trying to go from the ground floor to, up one flight of, or, one floor's worth of height without trying to just do literally a standing vertical jump. So the horizontal component of stairs is convenient. So when you're going, hi cat, when you're going across, move, the actual run part of the stairs, the angle part, is simply to make it easier. It's convenient when really the work that you're doing is the vertical part of lifting your sorry butt up a flight, vertically, either one floor or 2 floors or 3 floors. So think about going up like a stairwell in the middle of a really tall apartment building. You don't really think about how much horizontal movement you're going. What you're really thinking about is going up, like how many flight of stairs up are you doing? It's the vertical part that you're doing in the terms of in the work, not just the little zigzag of every forward step that you're taking. The forward part of your movement is really inconsequential compared to the vertical part of the work going upward. So in this case, work equals force times distance. So in this particular problem, what do we got? Well, we've got an 18-kilogram backpack, and we're going up 4 meters. So our distance here is 4 meters. We've got that part. So now the question is, well, what's the force? We don't have a force in here. So remember, what is the force that we're working against? You can't just put the 18 kilograms in here because that's a mass, and 18 kilograms doesn't fit directly into a force category. But what is the force that we're working against? In this case, the force that we're talking about is this one. We're actually talking about weight. You're working against the weight of the backpack. So what is FG? Well, the weight of the backpack is 18 kilograms times 9.81. That's how we calculate weight. And so that's one of the commonly done tricks in these sorts of problems when you're trying to figure out what they are. 18 kilograms times 9.81 gives you a weight of 170. I've got too many digits here. 177 newtons of weight. That's the actual how much this thing. The combination of this is 176.58. So when you're doing your force here, it's actually 177. You're moving 177 newtons of weight up 4 meters. So if I do that times 4, I get a total of 706.32. Man, I only have one segment here. One sig fig, okay, 700 joules of energy, basically. So that's not too bad in order to get it to go up one flight. So there you go. Again, a couple tricks in this one. Again, you're usually doing work against gravity, which is going to be the vertical component of its motion, and therefore the vertical component of whatever the force is. And then don't forget that when you're trying to calculate what weight is, you have to use mass times 9.81. All right.